For the ProLab lecture, it's a great pleasure to have Einat Aharonov with us. So I think many of you know Einat, but for the one who don't know her, she had a background in earth science with a PhD in MIT with Dan Workman and Peter Caravan. And we were at that time also in the same group that Eric, if I understand well. 30 years ago. Yeah, 30. And in general, now you are the professor in earth science at the Hebrew University of Jerusalem, but also a professor too at York. And I think you know this place and the people working at York since the time it was called PGP. And what I like is that you connect all the different parts of York. You work really at the interface between physics and geoscience. You also have worked with, I saw Renaud on the picture, so with almost everyone involved at York. And yeah, you are interested with the process that form rocks, also the process that breaks rocks during earthquakes, that form earthquakes. And Einat is visiting us today and regularly now also because she's part of the project Unlock, and we have a direct collaboration. I'm very happy with this. And today she will talk about granular material and how fluid and solid particles interact in the deformation of porous media. And yeah, looking forward to hear about the work.
Thank you. It's a great pleasure to give a talk here. I'm always honored to be here. It's a wonderful place, unique in the world. As Fabian said, it connects all of my interests. Yeah, all my everyone my interest is manifested here by some very interesting research. So I'm going to give a talk about the PhD of this guy, Shachar Ben Zeev, a talented guy who did a PhD with myself, Liran Goen, and Renaud Tussaud, which you all know. And here we're standing in front of a liquefaction feature. Maybe you remember this, those of you who've been in that conference of the network that we had on flow and porous media. So that's in the Dead Sea. These are liquefaction features. So to introduce what is liquefaction. So first of all, I want to introduce what is soil. So soil is basically, we view it as grains, and in between the grains there is fluid. That's true for soils below the water table. Nearly all soils have a water table that's a few meters deep, and below that everything is filled with water all the time. So this is how it looks, and on usual days it holds the buildings and pipelines and bridges. And the grains carry and support the weight of the grains and the structures above them due to their contact. They touch each other and they transmit the stresses. The static stress at each depth is called the lithostatic stress, litho for rock, and it increases with as the weight increases. Liquefaction is a process that occurs during earthquake shaking, and due to some process that we'll discuss, this increases the pressure of the fluid between the pores with shaking. So much so that the fluid pressure is enough to make the grains separate, and instead of the contacts holding the weight, now the fluid will hold the weight. And because the fluid has no frictional strength, it actually makes this behave as a soup. This solid fluid mixture starts to flow like a viscous fluid, and that's what's called liquefaction. And this is the building liquefaction. And now I'll show you a movie from IRIS. IRIS is the consortium of all the earthquake research in the United States, and they made this movie. It's from San Francisco in 1906, explaining liquefaction. Now you see below the surface, we have loose granular sediments, and there's water in the sediment, so we need this component. And then comes the earthquake. There's shaking off this granular fluid-filled sediment, and then it liquefies. And now the liquid emerges to the surface here in this picture, and the building sinks. And this is a true picture of the building that sunk in the 1906 earthquake. In that earthquake, many buildings sunk, but also pipelines floated due to liquefaction to the surface. And these gas pipelines burst, and there were a lot of fires in this earthquake due to that liquefaction. And what happens is that liquefaction is one of the major concerns of earthquakes. It's one of the major hazards that we must understand and be prepared to remediate or to be aware of. So here you see some liquefaction related phenomena. What you see here is a sewage tank. After the Tohoku earthquake, the sewage tank was buried, but because it's empty and it's lighter, during liquefaction, it behaves like a fluid, and then with this buoyancy, the sewage comes out, and that's why the buildings sink due to the buoyancy, and the sewage comes out. So here you see all these sewage coming up, and then there's lateral spreading of the ground following this Christchurch, New Zealand earthquake. Here you see, there are many pictures of buildings tilting during liquefaction. This one is from Izmit earthquake in 1999, and you can see the building is intact, but it just lost its grounding and sunk. And here you see this building, it should be like that. It's just that. So, in addition, you see compaction, I'll call it compaction, ground settlement, loss of porosity, okay? And for example, huge mudslides, because this liquefied soil can flow suddenly. So if it's sitting on a slope, it can suddenly lose its groundings and flow down slope with no resistance. That's what happened in the Palu mudslides in Indonesia, following a 7.8 earthquake in 2018. Hundreds were killed, buildings were covered. Here you see little mud volcanoes that appear after an earthquake. We had them in Eilat after the 96 Dahab earthquake in Sinai. Near all the hotels, there were little mud volcanoes that we could go and see, and they spew the water out. And it looks like a volcano, but it's made of mud. And here you see the paleoseismicity that was formed by liquefaction. Well, we haven't been there, so we don't know that's what happened, but the implication, the analysis that has been made regarding this is that on the Dead Sea, there is some very shallow dipping sediments, and when there was an earthquake in the Dead Sea, because the Dead Sea is sitting on a transform fault, then the sediment was liquefied, and you're seeing now how the sediment deformed as it was going down slope. So those are the deformation ways. So liquefaction risk is large, and it's growing because people all over the world are moving into cities, and megacities are usually on the coast, and land reclamation is expected to increase with people wanting more land. And those reclaimed lands are especially susceptible to liquefaction, and so we think liquefaction risk is going to increase in the future. So how is liquefaction explained traditionally? What is the physics of it? Well, usually it's the regime of engineering studies, not physical studies, okay? So let me just say that it was very hard to actually get it into some physics-based analysis to convince geophysicists that this merits some research. Because actually GRL, for example, we sent first a paper to GRL. They said, no, this is engineering. And we said, but this is like the most important geophysics problem in terms of hazards. Like, why are you putting it all in engineering phenomenology? We want to understand it. They said, no, it's like, we don't publish it. Very weird. Anyway, So this is the classical mechanism for soil liquefaction. The idea is that we have grains and we have fluid in between. And then comes the earthquake shaking. And here you see this signal. And the idea is that the soil tends to want to reduce its volume under cyclic shear. It wants to reduce its porosity. But effectively, it has undrained conditions. That means that during the time scale of this earthquake, which is very short, 1 second, 2 seconds, 5 seconds, the fluid cannot escape efficiently from the pores. And therefore, it's trapped inside these pores and its pressure is increased. So this is the idea of the undrainage. The pore pressure, then, if you effectively reduce the porosity, can rise to lithostatic pressures, and then you lose grain-grain contact. So this is from the Niigata earthquake in 1960 something in Japan. So just to convince you that this is indeed how we normally think and talk about soil liquefaction, I'll read to you something from the National Academy of Sciences and Engineering. They gathered all the engineers dealing with earthquake hazards to write some report on the state of art and practice and assessment of soil liquefaction. And this is the report that they assume a simplified stress-based approach, including horizontally layered soil profile, horizontal ground surface, vertically propagating shear waves, and undrained soil response. So this is inherent in how all this is done in terms of analyzing hazard for earthquakes. The problem is that many places it doesn't work. This is a cartoon of what it means. Like if you have loose soil and you're shearing it under the earthquake, then you compact it to a more dense configuration, and then the pores reduce in size, and you get increased pressure. That's the conventional idea. The problem with assuming undrained liquefaction is that the evidence doesn't support this always. Sometimes it does, sometimes it doesn't. And there are many features that are not explained by this undrained model. Let me show you a cartoon. No, let me show you a demo that's shown to students to explain what is liquefaction. So here you see a bus sinking in a sand that was filled with water, but you see that the water is coming out. You see it's drained on the time scale of this process of shaking. Let me show you from the Tohoku, a huge earthquake. Remember the Tohoku earthquake with the Fukushima disaster?
Earthquake right now.
So this is
Actually moving.
these are during the earthquake. He's photographing the cracks moving.
Cracks moving. That crack was not there.
This is the sidewalk. This is a can of Coke. So you're seeing the sidewalk.
I felt like I was drunk. I could see different parts. Like
So he's talking and it's
Wow.
still shaking.
there's water just coming up.
So water coming out. That's the reason I want you to see this movie. And we'll see more of it coming out as the earthquake continues, because this is still, so you can see these cracks breathing. See?
It's getting bigger and smaller, going back and forth. There is water coming up all over the park right now. Crack is just moving. Water, I don't know if water lines are broken.
He thinks maybe water lines are broken, but it's not water lines. It's actually water from the drainage process in the soil, and I'll explain what happens in a few minutes.
It's coming up through the sidewalk.
So there's water coming out here as it breathes, you know.
Building making a racket.
It's still going on. As the larger the earthquake is,
Seriously,
the
thought it
more,
was-
the longer the
I
shaking
didn't know
is.
what's going on.
This is a 9.0 earthquake.
I was just.
Okay. So soil liquefaction certainly initiates when pore fluid can easily drain out. So what is the mechanism for drain liquefaction? How common is drain liquefaction? So also the observations that are not explained by the undrained mechanism. There are many, I'll note a few. I'll go over only one because I don't have much time. It takes a long time. Well, the first one that is maybe the most important is that far field liquefaction occurs. That means that the undrained process predicts, explain it in a few slides, predicts that the liquefaction occurs in the near field that is about one fault length away from the earthquake. And then it fails to predict liquefaction further than that. That would be called the far field. So that is the prediction, yet the observations show that more than half of liquefaction events occur in the far field. So that's one very crucial point to understand and explain and predict. Then undrained liquefaction does not explain co-seismic fluid expulsion, and undrained liquefaction does not explain co-seismic compaction. And it doesn't explain liquefaction in pre-compacted soils. Well, in Kobe, I should say how people make landfills now, especially in Japan, like in Kobe. There's a reclaimed land, and in order to make it resistant to liquefaction, because we know that liquefaction occurs mostly in loose soils, there's a process that the engineers do, and that is to vibrocompact. They go with this vibrator, which is huge, and they compact the soil. And then they get to some compaction, they say, okay, now liquefaction won't happen, and we can build on it. But then this reclaimed land actually liquefied in the Kobe port in the 1995 earthquake that they had there. So we need to explain why that happened and predict, like, how should we do that, if at all? And then recurrent liquefaction events, which means you have a liquefaction event, and then you have another liquefaction event in the same place. Again, this undrained response predicts that this won't happen. So the talk outline is this. I'll first explain what is drain liquefaction mechanism and validate it, and introduce it to the compaction front model. Then I'll apply it to the liquefaction beyond the earthquake near field. So what is missing in existing knowledge of coupled granular fluid mechanics in general if I want to build a physics-based approach to this? So there's a formalism that was invented 70 years ago by Bio, and probably most of you know this formalism, and it holds for porous material plus fluids, but only for elastic porous material. In granular material, we have a lot of rearrangement, plastic porous material, and we don't have a formalism, close formalism for that, for this coupled deformation with the fluid. So we want to have a physics-based model to describe this. So we've built a physics-based model. We have some analytical results, but mostly we compare these n-member results to the model, which is based on a model that was built here first, actually, by some of the people sitting here. So this is the equations. Okay, so this is based on the work of Eric and Knut Jorgen Malloy and Renault. And finally, we came and did it for these fluids. And we have an equation for mass conservation of grains and equation for mass conservation of the fluid between the grains, and phi is the porosity. And we have the velocity of the fluid, and we have the velocity of the solid. And then there's the Darcy law, which means that the difference between the solid and fluid velocity is proportional to the pressure gradient. And then there's an equation of state, which says that the fluid density is actually proportional to the pressure with a compressibility beta. So the fluid is compressible. And when you do some algebraic manipulations, you get to this, and you assume that beta P is much smaller than 1. You get to this equation for the pore pressure, which is that the pore pressure changes with time due to diffusivity of pore pressure. And then there's a source term. The source term is the plastic deformation of the grains. So you have the grains here and the pores in between them. And when these grains compact, that means the divergence is negative, that's convergence, and the pore pressure will increase. And this is a divergence, and the pore pressure will decrease. And so there's a connection between the divergence of the solid and the rate of change of the porosity. So one can write a non-dimensional pressure equation, which looks like this. The same pressure equation for the fluid now is non-dimensional variables. And the controlling parameter is the de Boer number. The Boer number is a non-dimensional parameter introduced by a guy named Rainier in the 1960s. And it basically says that based on the prophet Deborah from the Old Testament, who said in her prophecy that the mountains will flow before the Lord, in front of the Lord. And yeah, that's her prophecy for the future. And it just means that the Lord has a long time scale to view the mountains. And this is this time scale, the forcing time scale. The diffusion time scale stays the same. But if we look at it for a very short time, then the de Boer number is actually very large. If we look at it for a long time, then the de Boer number is very small. And so that's the traditional history of this number, but we use it for comparing the diffusion timescale of the fluid, the pore pressure actually, versus the earthquake timescale. So this controls whether it's undrained. If the diffusion timescale is very long, it's undrained. If the diffusion timescale is very short, it's drained. So we will concentrate on the drain, the de Boer number being very small. And if we are in this situation, we can throw away that first term, and we have these last two terms. The diffusion is balanced by the source and sink term. And you can show that the solid velocity is actually proportional to the pressure gradients in the fluid. And that means that the grain sinking rate is equal to the fluid escape rate. And according to Darcy law, the fluid escape rate is proportional to the fluid pressure gradient. By the way, if you have any questions, yeah.
I'm interested in the diffusion time scale, and I was just curious about how did you calculate it, because there are some of the symbols I don't understand which one.
Right. So actually, this is a length scale
Uh-huh.
to which it should diffuse, but you can think that maybe it's the top of the box, but it can also be like a diffusion timescale to a front where the porosity changes. So that actually depends on how your system acts. So it's a distance, a characteristic distance to which the fluid has to diffuse in order to lose its pressure to a different pressure place. Beta is the compressibility, eta is the viscosity, phi is the porosity, and K0 is the permeability. And this comes basically from the Darcy law combined with the source term. And also there is the divergence of the fluid, which is given by the Darcy law.
So
And the gradients are scaled by this L.
it's a 2D diffusion or 3D diffusion.
This is a 1D diffusion, in
Oh,
fact. We're looking at so we're going to show in a few minutes, I'm going to show how the model can actually be, it's 2D. The numerical model is 2D. But everything has a symmetry in the x direction, horizontal direction. So in fact, all the analytical calculations can be done in 1D.
So in your equation, it's basically assuming that there's no random contact. So the solid velocity is set entirely by the liquid.
Right, so yeah. You'll see in a minute or two, but that there's a compaction front, and above it, everything is liquefied. The grains are falling basically together in a fluid that's going up because they have to. The fluid has to be exchanged with the grains as long as the grains are falling. And then there's a compaction front, and below it, everything is compacted and nothing moves.
Oh, so
So,
if your density just exceeds some critical value, you stop the grain. So
right,
solid is okay. Okay.
yeah, so that's what happened, yeah. But that's a story that will come. Engineers define this force that the fluid exerts on the falling grains as seepage force. Basically, this dP/dz exerts a force. And it drags actually the soil particles. And there is a critical hydraulic pressure gradient that if you get to that, which is basically the lithostatic pressure gradient, where the weight of the particles is counteracted by seepage forces, basically. So they hold it up. And this phenomena is leads to basically behaving as a viscous liquid, this whole granular material, and the engineers know it as quicksand. In fact, we had trouble discussing with engineers because they wanted to call it quicksand and not liquefaction, because liquefaction for them is just static, no flow. And they have a different name. Quicksand is when you have flow like that. But they consider it to occur in completely different places, and like in swamps or not. Anyway, so this is based on your guys' work, this numerical model, and it's composed of discrete element grains. So we have the dry granular material, and each grain I follows this equation with a new term which is coupled to the fluid, which says that the fluid exerts a grad P force on each grain. And then on top of this discrete element model, we have a continuum fluid model that sees an average permeability, average porosity, and average divergence of the solid. Okay, so we have this grid that on this grid, we calculate this. And the permeability is just Carmen-Cusini. And the coupling occurs via the porosity, the permeability, the divergence, and the grad P term. Okay? So this is the simulation setup. We have this column of grains. And at the top, it's free. There's no stress. Fluid has zero pressure. You see here the grains. Each one is colored based on the stresses it feels. Red is high stress. And if you have, and at the bottom you have no flow, dP dz actually equals 0. And we have shaking, which is horizontal. Delta x follows a sine wave with different frequencies. These are the model parameters. And the Bohr number is actually going to be smaller than 1. And we assume here that we're actually looking at shear waves that are coming to an impermeable bottom layer, and you're shaking this soil, exaggerated soil. The Bohr numbers in our simulations were calculated to be below 0.1. So all the simulations are drained, actually. And all the experiments that I'll show you are also drained. So I want to show you a movie of simulations. So this is the simulation. You see the bottom in the blue arrow, and the black arrows show the velocity of the grains. So what you're seeing is that initially, only the grains at the bottom are actually moving. The grains at the top are not moving horizontally because they're decoupled from the bottom. They're liquefied. They're just moving vertically. So with time, you'll see this compaction region, which is moving like a solid mass back and forth. It's going upwards. Okay, and you can see here depth. It's horizontally average depth sections with time. So you'll see at the beginning, at time 0, this is the downward moving velocity of the grains. And it goes from 0 to 1. So this is 0, no velocity of the grains. And here it's moving, it's scaled by this theoretical maximum velocity, which is due to the gradient, the lithostatic pressure gradient. So you see that with time, we have a compaction front that has a velocity which relates to the slope of this going upwards with a zone that is compacted at the bottom, and it gets fatter and fatter. And if you look at the pressure of the fluid in this situation, and this is the axis pressure above the hydrostatic, you'll see that in the compacted region, the pressure, there's no pressure gradient. It's actually, there's hydrostatic pressure gradient. And above this compacted region, there's a liquefied region. And this dotted line is a lithostatic pressure gradient. So it has a lithostatic pressure gradient. So a liquefied region, which is initially large and becomes smaller and smaller. I'll show you now part of it again. So you see this whole part is a liquefied region, and this whole part is not liquefied. And this liquefied region becomes smaller and smaller over time. And if we look at other measures, this is cyclic horizontal velocity as a function of time. There's a region of 0 horizontal velocity, and there's a region that moves like a solid body. And this shows the front, and then the downward velocity shows the front. And then the pressure gradient also shows the front. So this compaction front model says that we have 3 regions. One is that final porosity, we'll call it phi c. One is the initial porosity with which we initiated the system, and one is that in between region, that's the compaction front. And theoretically, we calculated what would be the front velocity, and it would depend on the difference between phi 0 and the final velocity and the final porosity phi c. Okay, and the pressure gradient and the permeability and the viscosity. The event duration, so if we're thinking about how long will liquefaction occur, it will depend on the front velocity. So the faster the front moves, the shorter the event is. And this is theory versus simulations for the pressure behavior as a function of time and depth. Now, Shachar went to Renault, to his Strasbourg lab, and also did for a year and a half some experiments on a shaking table. This is 3D. With a box that he could photograph all the positions of the grains and measure the pressure, and had a shaker with different frequencies, different amplitudes. And then we compared to the experiments. So that is the experiments. How it looks like. This is a high frequency. It's really not very interesting. You see nothing. Except you see that the compaction, it's beautiful experiments if you measure things like the pressure, but you see this compaction occurring during, that's mostly what you can see. We have several indicators that liquefaction occurs. One is that pressure reaches the lithostatic value. The lithostatic value here is sigma 0, so, and this is the dynamic pressure. So we're actually measuring, 1 is liquefaction and 0 means that it's hydrostatic. And you can see the simulations show, this is pressure in the middle of the box. Simulations show liquefaction until the front gets there, and then it drops to hydrostatic. That's the theory, that's and the simulations. And then we have the experiments in red. It also shows elevated pressure and then reduction to hydrostatic. Another indication is the theoretical ground settlement, which we measure with time in the experiments and in the simulations. Another indicator is the movement of the grains left and right, the horizontal movement. If the shear waves do not go through the layer, that means it behaves like a liquid. If they're able to move the layer, it's a solid. So you see at time 0, everything is liquefied in the simulation, and with time, these are the shear waves. With time, if you look at this time as a function of depth, you see that up to a depth of 0.7, it's solid and then it's liquid. The same happens in the experiments, but a less pronounced signal. And indicator number 4 for liquefaction. All these indicators are because we needed to convince the engineers that this is liquefaction, because they didn't believe us that actually all the measurements that we're showing are indicating liquefaction. So we had to go through a list of things that show. And one is like loss of shear modulus. This is in the simulations. So initially, this is the stress versus the shear strength. Initially, it's steep, and then you can go to huge strains with no stress. That's like the And now I want to come to the last part of the talk, which is the application to the far field liquefaction. So this is a result from Wong, 2007, showing hypocentral distance versus earthquake magnitude and liquefaction events. So each dot is a liquefaction event measured in the field. And let's say this dot is at earthquake magnitude 6 at a distance of 12 kilometers from the earthquake. They measured liquefaction. And the tilted lines are the calculated energy density, joule per meter cubed, that was felt at that particular location, that distance from this magnitude. Now, it's been established that undrained liquefaction can only occur if you have enough energy density. So experiments show that you need about 30 joules per meter cubed. And so he plotted This is about this gray line, and it fits about the distance of one rupture length distance. So undrained liquefaction can explain all these events, but the majority of events actually are away or at lower energy density and cannot be explained by the undrained liquefaction model. Those are these models, these observations that occur even at 0.1 joule per meter cubed. This seismic energy density can be shown to be equivalent to this peak ground velocity squared. So we took the data and digitized it on a histogram and showed the number of events as a function of the log energy density. And you can see that 61 of the events are unexplained. That's the purple, 61% of them. So how is liquefaction initiated below the energetic threshold? So it's been bothering scientists, and Wang suggested that maybe small energy events break some permeability barriers, and those permeability barriers blocked high pressure regions, and now that they're broken, you get a pathway for a high pressure fluid to escape and reach some soil, and that's what liquefies that region. But it would be a little bit strange that this would be the majority of the events, that this is how the majority of the events occur. We have a more benign explanation, and that is they occur in a low, they occurred in drained liquefaction. All of our experiments and simulations are actually conducted at an energy below 1 joule per meter cubed. So all of them are in the far field regime. They're all drained, and many of them show liquefaction. Here we gather all the simulations in purple and the experiments in red, and we plot them as their front velocity, normalized, doesn't matter, versus the energy density that they experience that we put into them. And you can see that all of them, they have the same scale, by the way, as the top plot. So all of them are in this low energy regime. And in addition, I want to discuss what controls this behavior and what does it mean. We have a front velocity, which depends on the input energy. The front velocity increases as the energy input into the soil decreases. So I enlarge this, and you can see that actually this normalized front velocity fits better a plot of against power density, which is energy divided by the cycle time, that T that we discussed before. But I don't have time to go into that, so that's this little thing, little insect. So what happens is that the front, it depends on this delta phi between phi0 and phi c, the compacted. So if delta phi is small, the front velocity will be high. So we find that as the energy of shaking increases, the final porosity decreases. So this is how it looks. This delta phi, phi0 is the same for all the simulations and the experiments we try, but the final porosity changes. That's why delta phi changes. And you can see that delta phi changes with energy, it increases with the energy. So basically this says that the more we put energy into the system, the more it compacts. Okay, so, but of course there's a limit. But we shake it, it can explore more and more metastable regimes, because granular material are always stuck in metastable states. And if you input more energy, it can explore more and more metastable states, and it can go to its minimum state or try to go to its minimum state. And also this fits better the energy density, power density. I won't go into that. So 1 over U front theoretically should depend on delta phi, and it does. according to our simulations, the theoretical prediction is the dotted line. So now we have a theoretical prediction, this dotted line, and versus energy density and versus power density in this inset. And we can explain this plot that we see in the experiments in the simulation, and we can also say something about the event duration, which depends on the front velocity. So in this very fast front, the event is very fast. There is hardly any liquefaction. It goes like zoom. In this regime, down there, the front velocity is slower, and you have longer liquefaction, and you have larger compaction. The higher the energy, you have larger compaction and long events. So in a way, what you see in this histogram is that the liquefaction disappears when the energy is too small. That means that because the energy is very small, your liquefaction events will be very rapid. They'll hardly change any porosity. You'll not see it. It won't cause the buildings to tilt. It won't really, it's not strong enough to impact society. But in this, the more energy you put in, the longer the duration is, the more the compaction is. Okay, so I'll summarize and say that the classical model for liquefaction requiring undrained conditions struggles to explain liquefaction beyond the near field. We find that liquefaction can initiate under well-drained conditions due to seepage forces. It shows pressurization, settlement, attenuation of shear waves, and degradation of shear modulus. It has a propagating compaction front, which is inherent to the process. And then the power density, energy control, porosity change, the front velocity and event duration, suggesting why the observed number of documented events decreases with the energy. And we suggest that natural liquefaction events will occur under a range of drainage conditions. We don't say that you don't have undrained liquefaction. Of course you do, but you also have drained liquefaction. And we think this will revolutionize the way that we calculate the hazards related to earthquakes. And we can also use this to explain recurring liquefaction and liquefaction in pre-compacted soils. This has been submitted to scientific reports. But I'll just say that, of course, you can understand that if the front didn't go all the way up, you can liquefy again all that region that the front didn't eat yet. Or if the front didn't compact it to a high energy state, then you can come with a stronger earthquake and compact the pre-compacted region to a higher energy state. That means a lower porosity state. So it doesn't take much to explain this recurring liquefaction with this process. So that's all I have to say. Thank you. Do you have any questions?